Okay, so today is May the 5th, and of course, we have another LeetCode daily challenge to conquer. And today's question is the number, let me check, number 45, jump gain 2. And it is a million questions, and I'm surprised that for number 45 million question, I actually have no submission record before, so I never tried this question before. So that get me wonder if I can solve this question in time. Um, because this is a jump game 2, so I probably saw the jump game 1 before, but I don't recall any jump game that I did previously, and I have never done this before. So let's just get started and see how do we resolve this problem. Okay, so let's read this question. So jump game 2. Given an array of non-negative integer nums, you are initially positioned at the first index of the array. So you start with the first index. And since it's a jump game, I guess everybody have to jump to the end, I think. So each element in the array represents your maximum jump length at the position. And your goal is to reach to the last index in the minimum number of jumps. You can assume that you can always reach the last index. Okay, so let's see the example 1. So the nums array have 2, 3, 1, 1, 4. So each element in the array represents the maximum jump length. So for the first one, which is index 0, you can jump to 2 steps, right? So you can jump to this. You can jump to 1, 2. So you can jump to index 2. And then so for the index 1, you can jump 3, 1, 2, 3. Oh, so it's already reaching to the end. So the answer is 2. So, and the reason is that the minimum number of jumps to reach the last index is 2, and jump 1 step to 1 and then 3 steps to the last index. So you first start from 0, jump 1 to the second one, the index 1, and then jump 1, 2, 3, and then you reach the end of the array. So for the second one, oh, there's a jump 0. Okay, so you might encounter something that is not able to jump at all. So for this one, yeah, it's still 2, right? So you still jump to the second, well, the number 1 index, and then you can jump all the way to the 0. So the constraint is that the entire array's length is less than or equal than 1,000, but it will be at least 1. So because you start with the first element, so it has at least 1. And then each number in the array has a range of from 0. We saw 0 in here, so that's a special case. And all the way to 10 to the 5. 10 to the 5. So which means there will be a number that will jump you directly to the end of the array, because the array's length limit is only 10 to the 3. And you got the maximum number 10 to the 5. Okay, and there's no hint. Oh my god. Okay, so since there's no hint, it's all by myself. So at the first glance, it looks like it should be a greedy problem, right? The only problem is, first, I don't know what attribute that I can greedy with. And the second, I don't know how to prove that's a greedy problem. So for example, for the 2 examples showing in here, we definitely cannot take the longest jump, because if you jump 2 to here, then your only choice is to jump 1, and then reach to the end. So you will need to take 3 steps. And it's worse for the example 2, because if you take the longest jump and you will jump to a place where it's 0, which you cannot even reach to the end. So, and remember, there is an assumption that you will always be able to reach to the end. So when you reach to a place that you are not going further anymore, then of course it's not good, not a good sign. So it looks like greedy, but it's not greedy, at least not greedy from the star by the distance that you can jump. So what we can do is then, if so, greedy is a special type of dynamic programming, right? So what if we do it using dynamic programming? Let's see. So if we using greedy, it's definitely gonna be linear, right? I think. But if we are using dynamic programming, for example, for this, for the initial 0 index, our previous jump is 0. And then because I can jump maximum to 2, so for the dynamic programming, I update the DP table, this to be 1 and this to be 1, because the minimum steps we take to reach to this point are both 1, right? And then we increment the index to 3, and then for the range of the 3 starting from index 1, we then go forward to update all of their maximum jump length. So we update this one and this one and this one. So the problem is, if I use DP this way, the entire time complexity jump to n squared, and that's not good. So, and I'm pretty sure by using n squared algorithm, I am gonna get a TLE, time limit exceeded. So although my instinct, the second instinct is DP, but it doesn't look like it works in here because it's n squared. Okay, so if for DP we can dynamically, well, not dynamic, we can definitely change it to DFS plus memo, because there will be a top-down DP, right? So can we do that? So for no, I don't think DFS makes any difference, because DFS we recursively call, and then we think that because if you are using DFS, the reason why you need a memo is that you only call per cell once, right? And then you call it and you calculate the value, and then you put the value into the memo table, so that after that, if you repeatedly calling the same cell with the same value, you don't need to calculate the amount, the result again. You immediately return the value from the memo. But the problem is, from my previous thought about dynamic programming, we keep updating each cell to their minimum value. So I will still need to visit every cell a couple times to make sure that they have the minimum value. So no, I cannot use DFS. So the minimum number of jumps lead us to BFS, because BFS is oftentimes used to find the minimum number to reach from, to go from one point to another point. So yes, we can use BFS, I suppose. And BFS, if you if in each level you only put the point into the queue, the node into the queue once, then you guarantee that you only visit the node once, right? Because after you visit it, you don't need to visit it again. So for BFS, you probably can have a set, and then after you enqueue the node, you also put the node into the set so that you make sure that you don't enqueue the same node again. So yes, we can probably use BFS, and then if we use BFS, we probably only visit each node once, and then this algorithm will be linear time. So now the only problem is the space. Can we use constant space? For greedy, it's definitely constant space, but for BFS and we have a queue, we have a set. It's not constant. Anyway, let's start coding first. So BFS it is, and the level, when we reach the end of the array, the level will be the result that we return. So okay, let's try BFS. Okay, so for BFS, assume that we have a queue. Do we need a queue? So let's have a queue first. So how to get a queue? So queue of integer QUE equals to linked list. So assume we have a queue, and then we enqueue norms 1. So that's the basic DFS if we would to do the DFS. And then for each, and then I have a level which I will later return. Right, so level equals to, so for now, if the array only have one element, so we return 0, right? So we start with 0 because there's no jump, 0 jump. And then I need a length. So that's the first level. Or no, I don't need the length. So a typical BFS now start with while Q is empty. So if the queue is not empty, then we have a length of q.size. And for int I equals to 0, I smaller or equal than length I plus plus, and then int cur equals to, do we need to enqueue or pop? That's the question. We have an array in there and we keep moving forward, right? So for example, this one we have 2, so we enqueue this one and this one. And this one we have 3 when we increment, and then we enqueue this one and this one and this one. But the problem is the first one, number 1, it's already in the queue. So that's why we need a set. But it looks like we don't need a set. We probably don't even need a queue because we are keep increasing, right? So we only need to have an integer to memorize what's the maximum index that we can reach. So for now, the maximum index we can reach is 2, so that means from now until index 2, all the element has been in Q. And then when we increment the index to here, it's 3. The maximum index will be 1 plus 3, which is 4, is here. And if we keep the integer 4 in here, which means every element with an index smaller or equal than 4 is already in Q. So we don't need a set. And we don't need a queue. We use these nums as a queue. Right? We memorize, now we memorize the end of the next queue, right? We only need to remember the start from the next level of queue. Then we have the next level of queue to traverse to. We don't really need to include the entire group of elements into a real queue. We can just use an index to memorize the start of the next level and the end of the next level. So this might be an overkill for the space usage because we don't need that much space, right? Why I need to include them and pop them out, or pull them out, over them and pull them out again while they are already in the nums. Yeah, right? But that confused me because I only know the traditional way of doing a queue for BFS. Should I finish this first and then transfer that to the... But this is confusing too. I mean, why do you need to over something that's already like in the array though? You have a like sliding window, right? To keep to... You have a sliding window to mark the start and the end of the next level. So that will be your queue. You don't really need to in-queue all of them. You just need a sliding window to in-queue to memorize the next level of it. Okay, so let's do it. So I don't need a set, I don't need a queue, but let's not, right? I don't need this, right? So what I need is level. I need start equals to 0. I need end equals to 0, right? So that's the first level. First level is the first element, level 1, which is level 0. Because if we return immediately, right? So what we need to do is while the last element has not been in queue yet. So we can change this to end is smaller than nums.length. Okay, so the start and the end will be our next level of the queue. Okay, let's do it. So the length will be end minus start plus 1. So that's the length of the current level that we are going to traverse. So for I equals to 0, I smaller, then we probably don't need to even have length, right? So we need, okay, so we need a star, we need an and, we need a next level star, we need a next level and. Okay, so let's do it. So star equals 0 and equal to 0, and then when we traverse each level of the BFS, okay, so let's make sure we are doing BFS. Okay, so we have this and that, and I need a integer next star equals to and plus 1, and then next and equals to and plus 1, and then we traverse this level, for I equals to start I smaller or equals to, okay, let's make and equals to 1. So I star I less than end. So let's do this. This is star, this is star, and so I from star, I less than and I plus plus, right? And then so the current number is nums I, and I need plus 1, I think. So the next and math the max nums I plus 1. Is that plus 1 confused myself? Yeah, do I need the plus 1? Do I use and as the end of the array or and as the start of the next array? Anyway, let's be consistent. So next end. So we extend the level of the next level, the end of the next level's queue, and then and that's it, right? And then when this for loop ends, we level increment, and then our star equals to the next end, our and equals to No. Confusing myself. Next, end. And then that's it. So if this is still smaller than no, yes, if this is it's still smaller than, then we keep going, right? Which means the last element hasn't been reached yet. But then if we eventually reach to the end of the array, then the next end we assign it to this, and then yeah, I kind of want to try it two more. So we start from here, which is level 0, and the star is 0 and is 1, and then level is 0. So we enqueue one, so we enqueue this 2. So now the next star will be end, which is here, and the next end will be here. So we increment level. And then level now is 1. And then we enqueue 1, 2, 3, 4. Enqueue 4 plus 1. Enqueue 4 plus 1, which is 5. But we then still increment the level. So I increment level too much. Of course I can do a break. Well, but I already have a while loop in here. So do I start with -1 and then I do a level plus each time in here? Does that make it look better? Yeah, but is this correct? So now if I only have one element, how's that? Yeah, it will. So I shouldn't do this. I'm confusing myself. So I shouldn't do this. So it's still easier to I don't want to make my code ugly, but of course in here I can check if this looks ugly, but I don't know what's the faster. It's like yep. And let's try the second one. Yep. And let's try a random one. What did I type? Oh god. No, it's wrong. It is wrong. Okay, so I have something wrong with my BFS. Why? Because I think, yeah, 4 is definitely correct, right? So I jump 1 to here, 1, 2, 3 to here, twice. Third time to here, and then fourth time to here. So why my program return 6? So for this we enqueue 0, 0, and then for this, and we increase one level in enqueue 1, 2, 3, and now it's level 2, and we enqueue this, this, level 3. So why do I reach to 6 though? Ah, I'm confusing myself. I just want to know. So yeah, the first level is 2, right? So I enqueue this 2, and then the second level I enqueue all the way to 1, 2, 3 here. And, oh, plus I, right? Uh-oh. Then each one of them is 1 too little. So now I have to remove this, right? Oh God, what did I do? Yeah, yes. So BFS actually works. So BFS, for what I can see, it's working as good as greedy, because I only visit each node once. I'm surprised, but I think this should pass, right? I use a random array and it passed, so I think this should pass. Let's try it. I shall pass. Okay, yeah. So I'm surprised that, let me check the result. I'm surprised that BFS work as good as, oh, everybody's the same, have the same runtime. So this indeed is a linear problem, algorithm problem. So everybody is able to do it linearly and use similar. Oh, but my space usage is worse than other people. Not worse by a lot. Yeah. But I'm surprised that BFS work as good as a linear algorithm, because it only visits each each node once, and I actually did not use a lot of space. I use constantly more of space than other people, I believe. So let's try to see the official solution. Yeah, greedy, but how do you do greedy though? I know this is a greedy problem, but how do you prove and how do you make it a greedy? If you are at this position in the array, then you can jump to one of the following 3 places. What would you choose? Of course, I would choose, no, I cannot greedily jump, right? So all those are just telling me that I cannot doing greedy based on the length that I can jump. So what are we greeting with? is my problem, is my question. So subarray of the current jump, and then next subarray of the next jump. But this almost looks like BFS, right? You have the subarray of the current jump, and then you put the subarray of the next jump, which is the next level in the BFS, right? Or did I misunderstand anything? Proof of correctness. They prove the correct. Yeah, for the greedy, you prove by contradiction. You assume that by making subarray for the current jump. Yeah, but I need to know which one are we greeting at first. To answer the question, let's think about in the following way. Our next move will fall somewhere between start and end, yes. And find the minimum number of jumps to reach to the end of the array. We must determine which place will take us furthest in the next jump, yes. As you may notice, we used greedy approach. Always jump to the place that will take us furthest. Okay. Greedy will always make the locally optimal decision. Okay. But then, yeah, do I need to check one by one in the next level? And do I need to come back? So if at any step we make a different choice than our greedy algorithm would make, we find a better solution of the problem. As shown in figure 3, I guess this is the figure 3. Consider two people A and B. A follow our greedy algorithm. So this is, which is A? This is A. So we jump to the one can take us furthest, which is the 5. And sorry. And then this one, the green man, the B, jump to other places. So we first assume that if by not doing our greedy, we can actually jump it further, and then we show it is not true. Then we prove it by contradiction. So this is their proof. But how do they prove that it's not true though? The number of each index of the mixed-on jump, let's assume that until that point the decision has been identical. So now let's make the jump difference by subarray next jump. The greedy solution always pick the largest subarray. Thus A will always have the largest subarray than B. Henceforth, it's not possible to beat the greedy algorithm. Okay. Yeah. So what they mean is that A follow our greedy approach, and then so our greedy approach is always jump to the one who can take us furthest from now. And then B is the contradiction situation that we assume that somebody did not follow our greedy algorithm but can jump further. And then because A, the condition is the point which can take us furthest, so no matter what B does, the furthest jump B can jump next step will always smaller or equal than A. The proof, I always think that it's a little bit tricky. Yeah, it's like, again, like to make an article to convince people. Like, yeah. So now we know what we should do by greedy, but how do we accomplish choosing the furthest one though? Algorithm initialize 3 integer value jumps to count the jump, current jump end to mark the end of the range we can jump, and the furthest to mark the furthest we can reach. Oh my god. So this is I guess that's why BFS looks so much like the greedy, because the BFS and the greedy actually, the thought process are different, but they work the same. I mean, the current jump end is in my BFS the end. The furthest in my algorithm is the next end. So it works the same way, although the thought process is different, but the greedy actually work the same way as BFS. Wow. Wow. Okay, I learned something today. Because for every time for greedy, I was just thinking that my math is not good enough for me to come up with a contradiction proof. And then I don't know what to base on when doing the greedy. And now this problem provides us another way of accomplishing greedy algorithm by doing BFS. Hey, Safine, how are you? So I don't know if you have done this before, but this is the first time I do this problem. And yeah, yeah. I just thought that I know it should be greedy. I know it should be linear, but I can't come up with a good idea to do the greedy. So that's why I choose to do BFS. But yeah, it end up we named the. Okay, cool. You have done that. Yeah, cool. So do you use greedy too? I mean, do you come up with the greedy idea? Because I can. I know it should be greedy. I have an instance that this type of problem should be greedy, but I can't figure out how to do greedy. That's why I do BFS. But somehow, because I want to save the space by not declaring a queue and declaring a set, so I use integer to mark where is the next level of the queue. It end up so similar like the BFS, so similar like the greedy. So I'm surprised. I like greedy though. The coding of the greedy problem is always easy. The hard part is to come up with the greedy idea and actually prove that it works. Oh, hey, there's a greedy solution. Let's check. Oh no, the BFS. Yeah, we have level, we have current max, we have next max, and we have I. Yeah. So other people's BFS also looks like greedy too. Yeah, but he returned level in here. But it's the same. I break, right? I break and return level. So yeah, it's the same. It's the same. Okay. Oh, hold on. I thought of ending the string. I saw something interesting here. Okay, I usually have a pen and paper to visualize which approach to go DP or greedy would be better for me. Yeah, I actually prepared something to draw, but let me check. I actually prepared something that I can draw in here, but I can't draw either. So yeah, so you just saw me keep talking because I am not good at drawing anything, although I prepared. Yeah. So yeah, let's check this idea. So from last to star, yeah, because there is another way of thinking greedy is that you start from the end, right? And you always jump to the furthest, to the leftmost position that can reach this point. So you jump, so you check which one is the leftmost that can jump to the end, right? And then from here you check what is the leftmost point can jump to this point, and so on and so forth. So this is another way of thinking greedy. Yeah, I think this matched to my original greedy idea more, but I I want this approach because I think this approach is easier, like easier to be understand as a greedy algorithm, because you can clearly see where you are greedy with, like what attribute that you are greedy with, right? You just greedy with the furthest point that you can reach every time. Yeah. So yes, but no. A while position is 0, 4. I from 0 to position, and then you position is I. Okay, before I end the string, I want to say this algorithm is not linear. I want to say that this is not linear. I might be wrong. Your position star backward, right? Your I star forward. You know what I mean? So you are essentially, the worst case could be n squared, I think. Yeah, so it's a good approach, but I think the implementation is probably not good. For each point you are going backward, you check again where are they, yeah, what is the furthest they can reach, right? So it's like in here, from here, you traverse this entire array to find this point, right? That's the first loop. And then from here, you traverse the entire part again to find this point. So in the worst case, in this, you traverse the entire thing again to reach the second point. In second point, you traverse the entire array again to reach the third point. So this is a good thinking, but a bad implementation. I mean, the implementation is still n squared. This is not linear. Yeah, so yeah, it just caught my eye that somebody draw a little bit drawing and it matched to my original greedy idea, but I don't think, yeah, but I give up the original greedy idea because I think the one that I thought of is n squared. And this one is also n squared. I think somebody might be able to come up with a better implementation, but yeah, but the original idea, the, the author who come up with the original idea, what does the repel say? The reply? That's amazing. It's hard to prove the algorithm using BFS. Oh, the replies just ignore what he said and keep implement with BFS. It's funny. Yeah, it's funny, right? Everybody just comment with BFS. Same idea, but I think mine is better to understand. Better to understand, but it looks like it's still the same algorithm, I think. For I equals to low. Yeah. Oh, 21st reply. Where's the 20? Oh, wait, did I skip any? So this I expand. Oh, hold on. Show 20. Okay. Sorry, my bad. So, oh yeah. Yeah, somebody reply it's n square. Yeah, and somebody implement the idea in Python. Yes. So this is awesome and so easy to understand. Thank you for all the people thinking. Oh, and check at the top. I don't quite understand Python. So what is the O and check at the top? not only it gets accepted. What do you mean by you can check on? I don't know. I'm not a Python coder, so I don't know what does this means to add an on check at the start. Really? He check ceiling length? What? Okay, I don't quite understand how he checked this. Return if the length set. Okay, if the length is less than 2, but what does he means by checking on though? I don't see it. I don't see it. But I am surprised that if he is using the same idea to implement. Oh, wait, but it's maybe because of the test case, right? Maybe they don't have a worst case as this. Maybe they don't provide a test case like this to make it run in the worst case, right? So you might still beat 99% of people in the test case only because that test case didn't include those type of test. That's what I guess. Yeah, but everybody say it's n squared, right? Yeah, it's n squared. So okay, maybe our next challenge is to see. I mean, I'm gonna end the string here because I don't know if I can come up with the idea. But maybe our next challenge is to check if whether we can like implement a linear algorithm to do this greedy. Yeah, that's what I think. Because I definitely think that this can be done in linear time. I just think that implementation make it worse. I mean, you can definitely check or prefill this leftmost array linearly. You don't need to check every time you jump to a new position, right? If you prefill another array with this number in here, although you waste a lot of space, but you don't need to check every time after you jump. That's what I think. Okay, so I guess. Oh, your approach? Let me check. Okay, let me paste it to the because I think the chat will disappear pretty quick. So how do I? Where is the playground? Okay. Okay, let me paste your code in here. Ah. Okay, so you okay, you have 3 of them, right? And then for this, and then if this so I is the index, so if I less if like larger than, then your jump will +1, and then your preview equals to cur. I guess this is your algorithm, right? Okay, or maybe this, right? Did I did one? Okay. Guess I mess up yours. Space or tab? Space. Okay. So I think you increment the jump if the I is larger than previous. Otherwise, your previous is equal to cur, and your cur is max I plus number. So you directly jump to cur, and then you let the previous. Oh, okay. Okay. So for each I, if you have the previous inside A, okay. So if your I is larger than the previous, you increment jump. Yeah, you increment your answer, and then yeah. And then you remember what is the previous, right? And then you update the curve to the max, and then you jump to that. Yeah, okay. And then you do the next one. Yeah, it's pretty clean though. Cool. Cool. Hmm. I larger than previous. Okay. Okay. Yeah, I'm trying to understand. So I larger than pre. So your pre is to memorize the previous maximum, right? So if your current one exceed the previous maximum, then of course you need to jump, right? So is that what you mean? So you jump only when the current one is already out of reach from the previous maximum. Is that the logic is? Yeah, so this is also a greedy approach, right? I think. Jump plus 1. Yeah, I'm just surprised that this is another different greedy approach. Yeah, I think somebody must use your approach. So you memorize the prior maximum, and then you check for each y, if for each I, if this I is out of reach, then you increment the jump by 1, right? Which means you need to jump. Did I understand that correctly? Right? Otherwise you don't need to jump, you just keep updating the current maximum. So let me go through the example of yours, I think. So let's try the test case. How many test cases that we have? Oh god, that erased my previous test case. So if I understand yours correctly, so you initialize everything as 0, and in here for the first index is not out of reach, so you only update the current max, right? So the current max will be this, which means you can reach to here, right? And then you increment I to here, and it's, hold on, did I understand it correctly? Because the first step, we update our current maximum to I plus this current maximum will be this, right? So when you increment I to here, it's still less than this. So you don't increment the jump, you don't update the curve, the previous one, but then you update the curve until this point, right? and then you increment this. Hold on, then when did you? Oh, hold on, I was wrong. The second one is already in here. You already jump once, right? And then you already update the previous to cur, and then you extend the cur to this. So you already jump once, right? That's when I equals to 1. You update the pre. Okay, let's try it. So wait, you didn't finish the entire thing, right? You want me to try this in here? You want me to try your code in here? I could, but did you like finish? Okay. Yeah, I just don't know if I did your code correctly, because I copy your code from the chat. Yeah, and you run to visualize the execution. Hold on, I shouldn't return jump, so do I print jump? Do I change it to print? Is that how you do in? Yes. And then next. Hey, why do I? Why I cannot see? Yeah, I should see some value changing, right? or or I don't. Close this. Where to close? Okay, thank you. Close. Oh God. Thank you, Deja, X Deja. Thank you. Oh, cool. This can visualize, right? So I1, and then yeah, you update the jump, and then your price set to 2, and your cur update to 4, I think. And then your eye will not be larger, and then your eye will not be larger. Oh, it's larger than previous one. Okay, so that's why you update the jump, and then you update the free to the last. Okay, I got it. Okay, now I got it. Yeah, I know curve will always be the max, but it just confused me about you memorize the prior curve, which is the prior max, right? So once you exceed the prior max, there is a jump. Is that what you mean by this greedy algorithm? Although you always, yeah. Okay, 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 okay. So you are doing what this is doing. You are doing what this solution is doing, right? So you are doing this. You are searching for this can reach this, and that this one here is your current max. This 5 here is your prior max, right? So and then so because not this one. So yeah, you are doing the greedy in here. Yeah, you go through the entire one, and every time you update the max, and then if you reach the current jump at, you increase the jump, and then you memorize the current jump at. Yeah, you are doing exactly what this is doing, right? So if I change to Python 3, it will be almost like your code, I suppose. Yeah, yeah, you're doing this in here. Yeah, it's only the order is different. You put this after the if, yeah, but you're doing the same thing though. So yeah, your code is the greedy. Okay, now I understand. Well, thank you for sharing though. Cool, cool, cool. Okay, okay, I got it. Yeah, and thank you for sharing this pythontutor.com where we can visualize the variable so that it's easier for me to not need to draw anything or put any comment to memorize the number. There is an automated tool to memorize the number for me. Okay, thank you, Safine, for sharing this. Yeah, okay, me too. I will end the stream here, and then I will see you tomorrow for another daily challenge. So thank you for watching. Goodbye. See you tomorrow.